I'm Dan Fylstra. I'm the president of Frontline Systems. We're known for one thing, for having built the original solver in Excel many years ago for Microsoft. And so I was asked to talk about building analytic and decision models in spreadsheets. So let's, first of all, make sure our cell phones are off, as you've heard all day long. And then let's dig in. So first off, my hope is that you will walk out of here with some real knowledge about what you can do sort of beyond playing what if in a spreadsheet in Excel. I'm only assuming that you do know how to build a what if model in Excel. And I'm not assuming anything that you know anything about even using solver or using Monte Carlo simulation or doing data mining, whatever. And what I'm hoping you will take away by the end of this session is to know what kind of results you can get from analytic models. And I'm thinking in a business sense here. Know why you'd build an analytic model. That is, what kind of business payoffs you can hope to get. Know how you would build that model. We're not going to try to teach you all the details of how you'd build everything, but you'd know how you'd go about it, and you know how it relates to a conventional what-if model. There's a whole topic of what not to do. There's pitfalls, and I'll try to give you some hints about what pitfalls to avoid. And one of those has to do with the solver model. Let me ask a question at this point. How many people have ever used the solver in Excel? You got a show of hands? Quite a few, but still maybe a third, looks like, maybe 30 to 35%. And of all those people, how many people have ever found that it was difficult to get what they really thought was the optimal solution, the best possible solution? Some. Actually, maybe about half of those people. Maybe about 40% of those people. And I'm going to try to dig in on that. That's actually maybe the most challenging topic to discover, but I want to give you some insight on that. Finally, I do hope that you walk out of here with some confidence about actually going out and trying this yourself. And my parting message will be kind of about that. So here's what we'll try and cover. In kind of part one, I have some PowerPoints, and I'm going to talk about what is different from a what-if model, a conventional spreadsheet model, when you're what I'm calling an analytic model. What kind of results can you get first from a Monte Carlo simulation risk analysis model? We'll tackle that one first. Then we'll go hands-on with a simulation model. And then about what results you can get from an optimization model. And then we'll go hands-on with a very simple, we'll actually go hands-on with three simple but different types of optimization models and applications. Then these will be small models for illustration purposes. Then we're going to talk a little bit about real-world models, which are typically larger and involve more data. So we're going to talk about getting the data. That's where we're going to use Power Pivot in the spreadsheet data model, and scaling up in size. Then we'll dig in with a model that is getting its data out of the spreadsheet data model, where there's actually 2.4 million rows in the major fact table, in that underlying spreadsheet data model. Then we're going to cover a topic that's kind of key to advanced optimization modeling using integer variables, in particular using them for yes-no decisions. Talk a bit about that. That will lead us into this topic of why you can't always get what you want from solver, what kinds of models are solvable to optimality, what kinds of models are solvable to like a good solution but not proven optimal, and so on. And then the final topic, which I hope we'll have time for, that depends, is optimization models under uncertainty. So we're going to combine simulation, which deals with uncertainty, and optimization, which deals with allocating resources to get the best result. And then we'll have takeaways and questions. If at any point you're stuck on the computers, just raise your hand. We've actually got, I think, 3 people in total walking around and helping people, 1 from Frontline and 2 people from PASS. And they are really knowledgeable, so please go ahead and raise your hand if you have a problem. And if you have a question for me, again, try to raise your hand and let me know. Just bear in mind, like if it's a question that can wait to the end, please wait it, hold it to the end. If it's really relevant now, then please go ahead and ask, okay? All right, so now I think we've done this part, the lab PC check. If all's well, the most important thing is that you've got Power Pivot and Power Query on the ribbon, and Analytic Solver Platform and Excel Miner Platform on the ribbon. And then if you go to the Data tab, you should have Solver over on the, on the right under the What If, or the Analysis group it's now called. And if those are missing, you can use these options to just turn them on. It's not hard. Anybody having a problem with that right now? Okay, sounds like we're in good shape. So let's go ahead and proceed. One thing I want you to understand is, let me ask this question. Back at your companies, how many people are still on something like Excel 2007? We've got just a few. Okay, we understand that. And how about Excel 2010? Quite a few, right. And then how many are on Excel 2013? Well, this is a select audience, compared to the broad world, more people are on Excel 2010. But that's fairly typical. What I want to say here is, I think one of the takeaways really should be, and hopefully from the whole conference, this notion that modern Excel is quite a bit more than just the spreadsheet with, 1 million rows, right? I had to answer a question from somebody a few weeks ago who thought it was still 64,000 rows, pretty old. But a modern Excel is much more than that. Modern Excel, Power Pivot is really the core of SQL Server analysis services, the X-Velocity engine in memory with Excel, the full power of that multidimensional BI database. Power Query is really SSIS. It's SQL Server Integration Services. It's the ETL, extract, transform, and load part of SQL Server in memory with you in Excel. Now, those two things, first of all, are free, and they're from Microsoft. They're from the SQL Server group. If you have Excel 2010, they're not built in, but they're free downloads. Just go on the web, search on Power Pivot and Power Query, download them and include them. There's just no downside to doing this. Even if you're not actively using them, having them around will be a help, and at some point you really want to dig in and use them. If you have Excel 2013, Power Pivot is in the box. It's pre-installed with Excel, and so is something else called Power View, which is very nice, but we're not going to use it here. And Power Query is still another free download for Excel 2013, so go get it, install it, and use it. Anybody in the room have Excel 2016 at this point, preview? Okay, so you guys probably realize that both of them are built in improved form in Excel 2016. So this is definitely something I want to encourage you to do. Okay, now the other software here is one of several options that you might have to build the analytic models, optimization and simulation models, more advanced models, and it's the software that I'm most familiar with because my company makes it. But that's not your only alternative. I'll certainly talk about other alternatives by name, but something else I want you to be aware of. How many people have an Office 365 subscription? Okay, about maybe 30% again, something like that. So if you have Office 365, you have access to Excel Online. And there's a new generation of apps, as Microsoft calls them, that are gradually replacing add-ins, which only exist in desktop Excel. So now the app facility is not as powerful as the add-in facility, but it's getting better all the time, and very soon it will be more powerful. So one thing you can do, so free alternatives to what we're actually using here, there's a free solver app for Excel, Excel Online, and it also works in Excel 2013 as long as your workbook is online. And then there's also a free risk solver app, which does Monte Carlo simulation, and you can just get that. These are both pictures from the Microsoft Office store. You can go and get that and add it to your to Excel and so on. The way you do that, by the way, is there's on the Insert tab in Excel 2013, also in Excel Online, you say Insert, and there's a choice for Apps. And you click on that, and then you can see apps that you have, or you can go to the store and find many free apps are free and others are paid. Okay? All right, that's all kind of prelude. Now let's kind of dig in on analytics and what it's all about. What you have on the screen there is the cover of a very influential book that was published some years ago by Tom Davenport and Jeannie Harris called Competing on Analytics. And it really got the attention of a lot of large companies because they saw how this really made a difference in like who was winning and losing on a large scale in businesses. This book starts with the story of Blockbuster Video. How many people remember that? Okay, and Netflix. Okay, and at the time, Netflix was the upstart, which was, they were just trying to like use the post office, right, to ship DVDs by mail to people. And they were going to compete with the biggest video, retail present store chain in America, Blockbuster. Are you kidding, right? Well, now we all know what the outcome was. But how did it happen? Well, Netflix did a number of things right, but one of the key things, Netflix has been one of the big contributors to predictive analytics. They built models to figure out what kind of movies their customers were watching and what kind of movies they would like next. And they did a better job of that. Blockbuster didn't have anything like that, right? And so Netflix gradually wooed more and more customers over to the Netflix way of doing things because they kept getting the movies that they really wanted to see next. And so predictive analytics literally changed that industry. So that Netflix is now the major force, the biggest user of bandwidth on the internet these days. And Blockbuster is no more. I mean, they're completely out of business. So this is the power of analytics. So now Tom Davenport, who wrote this book, also was probably the first person at least to popularize this taxonomy of descriptive analytics and predictive analytics and prescriptive analytics. So let's dig in on that a little bit. And this, you may have heard this a bit elsewhere in this conference. By descriptive analytics, we mean the quantitative assessment of past business results. So it's typically more than reporting, but as simply as dealing with past business results and either illustrating them visually with charts and graphs, or giving you summary statistics, or just doing exploratory data analysis. And then, so that's sort of the first phase. It's kind of the base for everything else. Predictive analytics, we're trying to go a step further. We're trying to use quantitative methods to predict new outcomes. And we'll talk a bit further about that. Forecasting, prediction, classification, and so on. There have been some other sessions on that. And then with prescriptive analytics, we're trying to build on those first two and actually use quantitative methods to make better decisions about things that are under our control, about like what products to make, where to ship them, how many to ship, what inventory levels to maintain, how many people to allocate to a shift, how much money to allocate to an investment project or to allocate to stocks in a portfolio, how much crude to bring into the different distillation units in a refinery, and so on. Okay, so let's drill into each of these now just a little deeper. So descriptive analytics, when you think about it, Excel and Power BI are really great for this. So the first problem is to get the data in, of course, in Power Query, which I was just telling you can draw data from all over, from many sources, everything from SQL Server and Oracle and Excel files and CSV files to Hadoop databases and HD Insight and Windows Azure Data Mart. All those things can be brought in to Excel. And then Excel plus Power Pivot is great for slicing and dicing, and you can summarize and you can do the nice things that you'd like, and Power View is great for data visualization, and Power BI lets you publish all that to the cloud. So this really covers descriptive analytics well. This is also where Tableau is a very excellent product, and there's ClickView and some other things out there. There's some very nice tools available to you in this space. Now, predictive analytics is sort of a generalization, or maybe just the popular new name for data mining. And here we are using past data, and we are constructing a model that we can use for prediction. But it's all driven off of the data. And one big difference here between predictive and prescriptive analytics is you don't have to design this model yourself, with spreadsheet formulas. Rather, what happens is the machine learning methods start with a general purpose model and fit it to the data that you give it. Okay? The machine learning algorithms are basically fitting parameters of a general model to your data, and then using that to make a prediction. So the general idea is we have something like, an example of what I mean by a general purpose model. People may have used LinST, linear regression, in Excel. What is LinST? Well, it's simply fitting a very simple formula, which is a sum product. It's just like the sum product function in Excel. All your independent variables, one argument, constant coefficients in the other argument. That's it. What the machine learning algorithm does, what linear regression methods do, multiple linear regression, is they fit all those constant coefficients to best account for your past data. And then you apply that to new data. So the data is things like, okay, we've got 1 million past credit applications. We approved a bunch of them, and we know from history how well those people turned out. Did they actually pay their bills or not? Okay, and so we fit a model to that data, and then we are going to use it to try to make decisions, classify new applicants into good credit risks or bad credit risks. We have 10 million telecom, cell phone contract subscription. We have data on all those subscribers, and we know how they use their phone and how much they're spending, and a lot of their behavior before they churned, or before they dropped us and went to a different carrier. And so we'd like to fit a model to identify, to classify people like you into categories of, are you likely to churn or not? And if you are, we're going to make you an offer before you leave us to try to keep you. Right? So there's a lot of like killer apps in marketing for predictive analytics. So these are the kinds of things we can do. We can classify, we can predict. Prediction generally means we take various explanatory variables and use them to predict one unknown variable. Forecasting, we don't have all those explanatory variables, but we just have something like one time series, like your past sales. So we're trying to predict your sales into the future. Or stock prices, we're trying to predict those into the future, or inflation rates or something like that. That's time series forecasting. And association rules involve, market basket analysis, recommender systems, and things like that. So we do all those with predictive analytics. And down at the bottom here, we have some of the tools that are available to you: Azure Machine Learning, Azure ML, Excel Miner, that's our product. Prediction Analytics is another product that's kind of Excel and SQL Server related. And then kind of the big boys outside of the Microsoft universe, SAS and SPSS and R are often used as these kind of tools. And there's more. I'm not listing everything, but those are all out there. Okay, now, a big difference in prescriptive analytics is that there's no way that machine learning can automatically construct the model for you. And why is that? It's because we're no longer dealing with past data and then just trying to forecast one new case where we have all that data again. Instead, we're dealing with your plans, or your business's plans, and your decisions about some future that, what you're going to do, what products you're going to make, or, how much promotion you're going to put behind certain products, or how much investment you're going to make. And so there's really no alternative but to build a model that describes that business situation. And we need people, we need good business analysts to do that. And one of the beauties of Excel actually is that it's a great place to build these kind of models. And probably, how many people have built some kind of a what-if model, like a financial projection, a budget projection or something like that? Okay, most people are raising their hands. So this should be familiar ground. And so what we're going to do is we're going to build on that. We're going to start with straightforward what-if spreadsheet models, and we're going to add some things to them, and we're going to get more advanced analytic results out of them. That's all we're going to do. The key step, though, is that the model has to capture the essential features of the business situation. So you need somebody who understands enough about the business and then understands enough about a modeling tool like Excel to express it in quantitative terms. And if you've built this kind of model, you probably recognize this. You have a relatively small number of input parameters and a lot of formulas, right? And then and typically there's intermediate formulas, maybe for months or periods or something. And then there's some final formulas. Just some of the formulas are the ones that you really care about, the outcomes that you're looking at. And you'll play what-if analysis. And it's not uncommon today, even for standard what-if models, to get their data from Power Pivot or from a database or something to drive that model. Okay, now, everybody should be familiar with, if we have the model, then we can ask what if. We can do a best case, worst case, average case, and so on. And people, I'm assuming you're familiar with that. Okay? If you're here, you should be familiar with that. What we're going to do is we're going to go a little further with that model. We're going to add a few things to that model, and then in the case of simulation and risk analysis, we're going to ask about what are all possible outcomes. So we really want a full exploration. We want the thing to calculate our model thousands of times, not just for 3 different what-if scenarios, and then give us a comprehensive view. And the goal there is to identify risks, and actually, once identified, to actually do something to mitigate those risks. And then in optimization, we're going to ask about some set of variables that we have control of, and there's many combinations of things we could do. And what we want the optimizer to find is, what set of choices can we make that gives us the best outcome, where the outcome is something we define with a formula that we're going to maximize or minimize. We're going to maximize profits as calculated in our model. We're going to minimize costs, or we're going to minimize risks. Those are the most common things. So here are some tools. Solver has been around for a very long time and built into Excel. What's Best is a commercial product that's an alternative. Our stuff, Premium Solver is like the next step up from Solver that we offer. And those are for optimization. And then Risk Solver and At Risk and Crystal Ball are all popular products for Monte Carlo simulation and risk analysis. You can find all these things on the web. And then outside Excel, there's a whole universe of these too, from IBM, SAS, FICO, that's the same company that does the FICO scores. And there's a set of these optimization and simulation modeling languages. And the modeling language is really an alternative to the Excel formula language. Okay, so now let's drill into this a little more deeply. Make sure we understand what these models are going to do. If you think about one of your own what-if models, a model where you've made projections and so on, and if you think about the inputs and the input cells and the formula cells, the input cells, and these are cells that just have numbers in them, you could classify them in 3 ways. One is fixed parameters that we can't control, we have to live with them, things like tax rates. If there might be prices, and if you don't have control of prices, then maybe that's a fixed parameter. We're going to leave that alone, can't do anything about that. But then we're interested in 2 other kinds of input cells in the model. One is parameters that change, that maybe vary a lot, that we cannot control. For example, demand for your products, okay? Interest rates, exchange rates, your competitor's price, your competitor's promotion budget or something like that. These are things that you cannot control, that they vary, they have many possible outcomes that can affect your results, your business results, and so we're going to model that and do something about it. And then the third group are inputs that we can control, and they represent decisions we can make. And most often, those are resource allocation decisions. Like I was talking about earlier, how many people will we allocate to this shift? How many dollars will we put into this project? How many products of this type will we manufacture? And so on, okay? So just think in those terms about your model. Sort of step back and just look at it that way. And then on the formula side, we're going to have intermediate formulas that are just part of the overall calculation that we don't really care about further. We're going to have some top-level results that we are interested in. And in simulation, that's what we're going to look at as the outcome of the model. In optimization, we're interested in 2 other kinds of results. And this is just what these results mean in the business situation. One is results, things that we calculate that cannot exceed certain bounds. Like we have, we're building parts out of inventory. We'll see this example in a while. We have certain parts on hand, and we have a limited supply. And so we're going to calculate how many parts we're going to use, but we're going to place a bound on that. We're not going to, we can't allow, an outcome that uses more parts than we have. We have so much cash on hand. We have so many people on hand that we can allocate and so on. And then finally, we have a result, typically a formula cell, that we're just going to say that cell, we want to maximize it or minimize it. And then both of these methods, simulation and optimization, are going to calculate the model automatically thousands of times to get our results. And really, they're calculating the model just not brute force, but hopefully intelligently to get the results. But then we're going to look at sort of the summary of what we get. So what are those results? For a simulation model, we're interested, first of all, in the full range of outcomes and their likelihood. So now we can go to, if we're going to management or something, we can say not just, well, we ran, best case, worst case, average case, here's what we got. Now we're going to be able to answer a question saying, we looked at basically we attempted to model all possible cases. And now we can say something like, okay, we've got a 60% chance of making $100,000 or more, but now we're going to say something else about the other 40% of the cases that can happen. So you can give a full characterization of the results. And then we can do sensitivity analysis. For an optimization model, we're interested in finding of all the possible ways we could allocate our resources, what gives us the best attainable outcome. There was a feasible and optimal solution. Feasible means the constraints are satisfied. We're not going outside the bounds. And optimal means that the objective function, that formula cell, is maximized or minimized. And then we're going to get sensitivity analysis on the optimal solution, which tells us something else about marginal values in an economic sense. When we try to solve a stochastic optimization model, and we'll see if we get there, we're going to do both of these things at once. Okay, we're going to try to get best values, best possible decisions under conditions of uncertainty. Okay, so now we're about to get into our first example here, and we're going to do a little simulation model. And so where would you use this? It's in any business situation which involves uncertainty, and that's probably most business situations. So it's a question of the degree of uncertainty and how important, how sensitive your business outcomes are to the uncertainties that you're modeling. So they can be things like demand, weather, interest rates, and so on. We're going to represent those with probability distributions. And then we're going to get some, then we're going to calculate, we're going to sample those distributions many times and get results, and then look at our, and we're going to learn something from those overall results. Very heavily used in industries with high uncertainty, just like you'd expect. Oil well drilling, pharmaceutical clinical trials, aerospace, and so on. The whole insurance industry in many ways lives on this. They have to, because intrinsically insurance is dealing with uncertain situations about accidents and hurricanes and people's lifespans, and so on. It should be used in a lot of other modeling situations, and it is becoming more and more popular over time. So let's go ahead and give this a try. Now, here we are in Excel, and we're going to come to this other spreadsheet in a minute. But if you want to do this, you just go to Open, File Open, and then we're in a folder which is called, it's on the desktop, and it's called What If. Did everybody find that folder? Let me actually go to the computer and say, it's this folder. It's on the desktop, and it's just called Beyond What If. And then inside that folder, we've got these models.
I think it's in the D drive, actually.
Maybe on these machines it's on the D drive? Okay.
Yeah, so try the D drive. Everybody, if you wouldn't mind going to the D drive. And I believe you'll find his name on the D drive. Is that correct? Yeah, that's right. Great.
Good. Okay, so now how many people flew in here, on some airline flight? Almost everybody, right? So most of us who fly very often have run into this problem. This is from the airline's point of view, this is the revenue management problem. This is the overbooking and bumping people in no-shows problem. Again, from the airline point of view. Okay? It's a very simple what-if model. We have a flight taking off with 100 seats. We're selling tickets for $200 each. And we're operating under rules where if somebody doesn't show up for the flight, we can't just keep their money. Okay? And as you know, on most airlines, you can actually fly on another flight. And so you kind of get the full value of your ticket back. But we're assuming in this model that we just give a 50% refund to no-shows. And then if you actually bought a seat and you don't, we overbook you and bump you, then we have to pay you overbooking compensation. And that in this model is just set to a parameter of 125% of the ticket price. So these are just interesting parameters, and obviously you could play with those. Now, the key uncertainty in this model is what? Anybody? Number of no-shows, right. So we don't know that, and we could sit here all day long with little what-ifs. In fact, if I overwrote this cell, I wouldn't recommend doing it. There's a formula in it. But we could change this and try 8 or 9 or 4 or 5 or some other number of no-shows, and we could calculate our total revenue at C15 in the bottom. But what we can actually do right now, because what's in this cell is a formula with it's a UDF, Silog normal, and it will generate a random sample every time you press F9. So go ahead and try that. If you press F9, you see now we've got 14 no-shows and 5.9, and it's getting rounded to 10, and then 3, and then 10 again, and then 21, and so on, okay? So that's how the model is set up right now. Now, what we want to do is run a lot of trials and get an overall result. So just go to the tab Analytic Solver Platform, and it should pop up this little side window that shows the model in a large spreadsheet model, lets you navigate to where the uncertain cells are and where the outcomes are that we want to see. Okay, now the first thing we're going to do is just run this to get the results. So you can just go to Simulate on the ribbon here and click Run Once. And it should pop up a window like this. Okay, now I'm going to keep going because in order to even begin to keep up with time, I'm going to have to. So what's on this graph now is we're observing what was in cell C15, I believe it is, and it's run 1,000 different what-if scenarios. Every one was simply a what-if, a spreadsheet calculation, and then collecting, saving what happened in cell C15, and then plotting it. That's really all that's happening in Monte Carlo simulation. The key step is that what happens in the input cell, where we have that Silog normal function, is that representative sample values 1,000 times are selected for the number of no-shows. That's really the key thing. Then we just calculate the model each time, and we observe the result, collect all those numbers, and then plot them and compute statistics. Like the mean revenue was almost $19,000, standard deviation was $622, and then we have this distribution of outcomes. Now you can do this or not, it's optional. It's just to, I'm just going to use this for illustration purposes. I'm going to put a marker on this chart by going to markers, clicking the plus sign, and I want a marker at $19,000, and I'll apply it. Okay, that's it. Then I'm going to actually go back to statistics. Okay, and all I did is I want a fixed anchor point on the spreadsheet there. Okay, now we ran one Monte Carlo simulation. I just closed that side window and spreading out the chart. And so we now know what happens if we sell 100 tickets. Okay, we're going to earn about $19,200. Yeah, I mean, the real number I should show you here is this contains a little function called sign mean that calculates the average or expected value of revenue across the 1,000 trials. Okay? So that's what we're getting if we sell 100 tickets. But is that good from the airline standpoint? Would you ever do that if you were an airline, if you had no-shows happening at all? I mean, really, no. And because every flight will take off with empty seats. And from an airline's point of view, seats are like inventory. And when the flight takes off, that inventory is lost. It's perishable inventory. So from the airline's point of view, you really want to fill those seats. So it absolutely makes sense for them to overbook the flight, as long as there's likely to be any no-shows. Right? In fact, we can test this. All we have to do, I'm going to show you how to put this into what we call interactive simulation mode. So if you're at this point right now, just click on the light bulb where it says simulate, and it should turn color like that. And now we're in interactive simulation mode, which means that we can change things on the spreadsheet, and anytime we change something, another simulation is run, and the chart changes and so on. So I'm now going to ask, what if, under conditions of uncertainty, I'm going to ask, what if I sell 110 tickets? I just type 110 in. And boom, we run another simulation. And if you noticed, everything shifted over to the right. The chart shifted over to the right. Is that good? Is that good? Yeah, I see lots of people nodding. Sure, revenue, the distribution of revenue, we can earn not much or we can earn a lot, but the whole thing shifted right. This is what we're looking for. Let's try it again. I mean, if 110 is good, maybe 120 is better. 120. Okay, that actually, maybe that still looks good. It's a little less obvious. So let's go for, really a lot and say we sell 140 tickets. How does that look? Let me see, now it's not so obvious that that's better. And if you notice, we're earning 20,063. That's the average. And if I hit Control Z, which actually will undo, now it goes up, 20,598. Control Z again, it goes down again a little bit. Now I'm going to show you something else that's happening here. If you go to the very last tab here, these tabs show you different views of what's going on in the model. But the very last one shows a scatter plot. And if you click it, it will actually get bigger. This is a scatter plot of no-shows on the horizontal axis and revenue on the vertical. Okay? And right now we're selling 110 tickets. So did everybody see what's happening? Hopefully you get some insight from this. I'm going to change it to 100. And now look. More no-shows, less revenue. And that should make sense to you, right? Because we only sold 100 tickets, and the more people don't show up, the more empty seats we take off with and less revenue we get, right? But if we overbook, then for a while, more no-shows means more revenue, and then less again. Okay? So right now, hopefully you're just getting a little bit of insight from this. Please turn off interactive simulation here. Just click this light bulb again so the light bulb goes off. Leaving that on is a mistake people sometimes make. And now what I'm going to do is I'm going to go a little fast here, and you need not follow me on everything here because I'm going to try to speed up a little bit. After a while, that what-if analysis with uncertainty is very nice, and I can get some insight. But after a while, I kind of want to automate that. Okay, so now what I'm going to say is I want the software to do this for me. So in this cell C11, which is the number of tickets sold, I'm going to put a simulation parameter, and I want it to vary the number of tickets sold from 100 to 150. Click OK. So now I have a little SciSim param function in there. And now if I ran 2 simulations, it would run one with 100 and one with 150. And if I ran 3, it would run 100 and 125 and 150. If I run 51, so I'm going to go here to Platform tab and make it 51. Now the first simulation will have 100, and then the second simulation will have 101, and so on. Okay? So now if I click Run Once, I actually run all 51. And right now we're looking at the 51st simulation. We can look at that one, and we can look at the 40th. We can look at them all here. Here's the second one, and so on. And then we can actually, just canceling out of that, we can actually examine these things on the spreadsheet. Like here's simulation number 3, and here's trial 1, trial 2. We can look at them all. All the data is still there. You can see it changing. So that's kind of interesting, but more interesting would be to look at all these results at once. And so I can use charts, multiple simulations, trend chart, pick all 51 simulations, click OK, and I get a little chart like this. And now it's just plotting all the data that I collected on all 51 simulations. During the simulations, we were varying the number of tickets sold, and then each time we changed the number of tickets sold, we ran 1,000 more trials. Okay, and then we just collected the data and plotted it. And you can see that we're kind of peaking out. That the blue line is the mean revenue, and then we have above that the 75th and 90th percentile values of revenue. And we can see it's kind of peaking out around 116, 117 tickets. So now we've really got something useful if we're the airline, right? We have an idea how many tickets we should sell for this flight, and it's probably going to be different from every other flight. But actually, why should we eyeball that? Why can't we automate this whole thing? Because what do we really want? We want the number of tickets sold that will maximize expected revenue under uncertainty of no-shows. And that's not too hard to do. Well, what we need to do here is, first of all, set this back. You don't have to do all this right now. I'm just going to set this back to one simulation at a time. And then here, I'm just going to type over that sci-sim-param formula and just make it 100 again. So it's a number. And now I'm going to set up an optimization problem. Okay? So this is what I want to change. So that's a decision variable. So that's a decision variable. Click. And now it's set up. It shows up over here as a decision variable. And what do I want to maximize? I want to maximize expected value of revenue across the simulation trials. So I'll go to Objective, Maximize Normal. Okay. And then over here, I just want to check one thing. I'm going to uncheck that box. I'm going to run the LSGRG engine, the same one it's a version of the thing that's actually in the standard Excel solver. And then I'm just going to click Optimize. I'm in guided mode, so I'm going to get something that explains to me what's going on here, but I'll skip this right now. Just let it run. And sure enough, it comes out with an optimal solution. It comes out with about 117 tickets sold. So that's the sort of thing you can do. And I know I did that a little bit fast, but I hope you can see what's possible. What kind of business results you can get from it. Okay? Everybody's with me okay? Good, okay. All right, back to PowerPoint, and then let's talk about what we hopefully just learned. So we started with a regular what-if model. We did one kind of magic thing. We put that sci-log normal function into the input cell to generate appropriate random samples. And then we just picked an output says that this is what we want to observe. And then the software, the Monte Carlo simulation software will do the rest. And At-Risk will do this, and Crystal Ball will do this too. Ideally, we would actually calculate literally all possible values, but that's actually too many, even for a little model like this. And so the trick in Monte Carlo simulation is to draw a representative random sample of all the possible outcomes, enough so that you actually get coverage of all the possible outcomes, including the extremes, and then show you those results. And so we do things with Latin hypercube sampling and so on to ensure with high probability that you get that outcome. And if you want, you can run more trials. We could easily run 10,000 trials or something, or 100,000 trials. And then we examine the results using statistics and charts and graphs. But it's still, it's you who needs to turn those charts into meaning, into insights, into what it's telling you about the business situation. Okay. Now, what is involved? Like if you were to go out and do this, what's involved in building this model? Well, it really is just a what-if model, and presumably you already know how to do that. So the key step is defining probability distributions for, first of all, you would need to identify the things that are really uncertain in your model. And then you want to be able to define appropriate probability distributions. A very common way to do this is if you have historical data. So if you're an airline, you probably would have many, many instances of this flight taking off, and you'd be able to see the results. And just quickly, again, don't try to do this yourself, but I'll try to do it quickly. I've got another version of this model where I actually have some historical data. And so there's a tool in here, and this is what you'd probably really do. You'd click here, and let's see, Control-Shift-Down, should select it. And I go over here, and I've got this little fitting tool, and I'll ask it to run this. I actually want to use this kind of statistics. And it shows me now candidate probability distributions that fit this data, okay? And I can either pick the top one, or I can actually examine its fit and so on with these other charts. But it's showing me log normal. Why didn't it choose normal, by the way? What would be inappropriate about a normal distribution here? Everybody's heard of the bell curve normal distribution. Why would that not apply in this situation? Infinite in both directions, positive and negative. We don't really have negative number of no-shows, right? So that it would not be a very appropriate choice. So it's finding, like all the sample data is non-negative, so it's finding a distribution that fits that. Now what we actually did here, by the way, this shows us, okay, log normal with a mean of 10 approximately and a standard deviation of 6 is about right for this data. That's not actually what we used in the model because we thought about it. And that's what you need to do. What's actually in the model here is 10% of C11 and 6% of C11. What's the 11 number tickets sold? If we sell more tickets, will the number of no-shows go up or not? Just think about that for a while. And you can probably convince yourself it should be proportional, right? So we incorporated that into the model. Well, that's just a little bit about the skills of simulation modeling, and hopefully that's helpful to you. And if you don't have historical data, there are some options. You can usually find that a lot of people have done this in the past, and so there's literature on it, and you can find out types of distributions appropriate for certain things like failure rates and waiting time in a like a retail clerk situation or a bank teller situation, whatever. Okay, pitfalls. Here's some things. So another thing that you typically have to look out for in a model is you have more than one source of uncertainty in the model, and they are interdependent. Okay? So the pitfalls are either missing that when you need to incorporate it, or accidentally incorporating the dependency when you didn't mean to. So an example of this is, supposing in my model I had stock prices, and I had oil industry stocks, and I had airline stocks. And both of them, I'm modeling them as random variables, and they're all changing and everything. But are they unrelated? Are they independent, statistically independent? Stocks, they don't bear no relation to each other. Everybody's everything's shaking heads, right? So they're both highly sensitive to the price of oil. So oil price goes up, the oil company stocks go up, the airline stocks go down. Okay, and in particular, airline stocks and oil stocks are negatively correlated. So we need to incorporate that into our model so that we more accurately reflect what's really going to happen. Now, a pitfall that you want to avoid is introducing a dependence when there isn't one. Say you have two completely independent sources of uncertainty, but they're both being modeled by, like, say, normal distributions. So you've got like psi normal over here in your cell, or risk normal for using at risk, or something like that. And you say, well, that's in A1, and so over in C1, I also need that same thing, so I just say equal A1. That'll work, it'll appear to work, you'll see it on your spreadsheet. There's just one problem. They'll all be in sync. Every random sample in A1 generates exactly the same value in C1, and you've created two variables that are not independent, they're 100% correlated. Everybody see that? So these are just hints to, if you go out and try this, to bear in mind. They're probably the most common things where people run into problems. And then finally, when you're presenting results, a trick is to get, like management, to think in ranges instead of single point values. Instead of give me a number, you've got to reply with something like, okay, I'll give you the number, $100,000 with 60% chance. Would you like to hear about the other 40% chance? And hopefully, it changes the culture of a company when the decision makers all start thinking in terms of ranges. or in terms of distributions of outcomes. And what very often happens in these kinds of models is that people are surprised when the model is first run, and usually they're surprised because the extremes are either better or worse than they expected. In fact, that's really the topic here. What can this do for you? Well, if you can do this well, first of all, you're going to show analysis that's better than the typical spreadsheet what-if, best worst case. Avoiding surprises is kind of a big thing. How many have ever had a spreadsheet best worst case analysis and then the actual outcome was worse than your worst case? Yeah, I got a few hands coming up. And that typically happens when there's too many inputs for you to consider in your what-if analysis, and something actually happens where they all go against you at once. Something else can happen, and it often gets overlooked. There is a best case that's better than most people anticipate. It's where everything goes for you at once. And you actually want to look at that if you want a complete analysis. Then, sort of stepping back from this, you can, we haven't shown this in this example, but you can do sensitivity analysis on the uncertainties. And you can find out what uncertainties actually really impact your results and what others have only a minor impact on your results. And that gets people paying attention to the things that they should pay attention to, the most important ones. If you are negotiating, and very often in business we're in this situation, we're negotiating with someone, and we're negotiating about something where there is uncertainty. We have a customer they're a very large chemical company, and they're major suppliers to a whole bunch of very important customers. And the customer's demand is very uncertain, and there's also uncertainties involved in the supply. And so that whole negotiation process, first of all, if you've done the analysis and the person across the table has not, you have an information advantage. Sometimes it pays for you to share your information because you end up at a better place, more realistic place in the negotiation because you did the analysis of the wide range of outcomes. You explicitly modeled risk. And then finally, anyone who has sort of risen in the ranks probably already knows this. The higher you go in management, or the higher you go really in any company, the more you're dealing with uncertainty. So these kinds of decisions are things you just have to deal with, and if you can quantify them, you're way ahead of people who are basically making decisions to seat of the pants. All right, well, hopefully that's motivation to learn something more about simulation risk analysis. What can help even more in your career? Well, now this introduces the subject of optimization. So what would probably help even more is if you save your company a few $1 million. We have a lot of customers who have done exactly this. 3 months at a time, I can think of one guy, and I can see him in my mind right now. 3-person months, $3 million saved. Second round, another $6 million saved. He's a hero. They don't actually pay you the extra $1 million, but you might get a promotion or something. All right, so even better than that is to show your company how they can save a lot of money without investing a lot of money. And very often that can be done with optimization. And how do we do it? We take all the decisions we're making now about how to apply our resources, how to allocate them, and we find a better way, just kind of rearrange things, and that saves money with no capital investment. So what's in an optimization model? The things we talked about. Input cells that we're going to treat as decision variables. They're the amount of resources allocated to some purpose. Then we have formula cells that calculate something that represents how we're using up some resource, typically, that's limited. Inventory, cash, staff, people, vehicles that we're setting out on routes and so on. All these things are represented by constraints. Physical space in a warehouse. And then our objective is something we can calculate, formula cell, to maximize profits or minimize risk. Lots and lots of applications. So let's try this. So the model that we're bringing up now, if you'd like to do it, is called conventional examples. It's conventional optimization. You should find it in the same folder. And again, I'm going to speed up a little bit here, given where we're 1 hour in already. So this is kind of the simplest kind of a manufacturing optimization example. This is a little company where we're making 3 products, TV sets, stereos, and speakers. And we're assembling them out of 5 kinds of parts: chassis, picture tubes, speaker cones, power supplies, electronics. And if we can make one of these things and sell it, we earn $75 for a TV set, $50 for stereo, and $35 for speaker. And so this is going to be our objective, which is just the sum product of how many we make times these profit margins, right? Hopefully everybody's familiar with the sum product function. Now, as we make them, to make one TV set, we need one chassis, one picture tube, 2 speaker cones, and so on. So over here, we're calculating how many chassis we use up. So that's just the sum product of these times these. How many speaker cones we use up, sum product of these sort of bill of materials times the number we make. That's the whole model, right? Simple enough. Normally, we would get some of these things like the inventories on hand. We'd get that from a database or external source. And the bill of materials might be more stable, but we'd still get that ideally from our bill of materials system. Okay, now, how many people have the standard solver installed and available now? Okay, so if not, don't worry too much about it. I just want to show you solving this with a standard solver. That just means you go to the Data tab, click on Solver, and this model comes up because it's already defined. Now, the only difference between the basic spreadsheet model, the what-if model, and the solver model is what you see in this dialog. It's certain cells are pointed out that are going to play certain roles. That's it. Okay? So what do we have? We have up here, set the objective D18 down here to maximum. We want to maximize that objective by changing D9 through F9, how many TV sets, stereos, and speakers to make. And then we've got 2 constraints. We've actually got a constraint that says, don't make a negative number of products. Turns out you have to tell the solver that because although that might be obvious to you, in the real world, it's not obvious to the algorithm. You have to tell it, no negative numbers of products. And then this is just a constraint that says these 5 cells are element by element less than or equal to these 5 cells. The inventory is over here. So those are where we're placing on the bounds. Okay? Everybody with me? I think so. And so this is a linear problem. We can solve it with the simplex method. So we click Solve, and we get a solution. I hear it all over the room. And now we're making $25,000 by manufacturing 200 TV sets and 200 stereos. Now, that's nice by itself. And you'll notice over here that we've used up all the electronics, and we've used up all the speaker cones, and not quite all of the other parts. And we can't actually do better than that. Now, I'm going to run this one more time. You don't have to. You can if you want. I'm just going to solve it again. And this time, I'm going to ask for a sensitivity report. And this is something a lot of people don't do, and it yields a lot of interesting information. What the sensitivity report is going to tell you is, all right, this is the optimal solution. What would change at the margin if I could change some like my product profitability, or I could change if I could get more chassis or picture tubes or TV, or electronics or something. So over here on this tab, sensitivity report, we have shadow prices. And 2 of them are non-zero, and they are the same 2 where we used up all the parts on hand. Okay? And the numbers there, 1250, that means if we could get one more speaker cone and use it, we would make another $12.50. And if we could get one more electronics unit and use it to build product, we'd make $25. Up at the top here, we have notice we're not making any speakers. That's at its lower bound of 0. And so this reduced cost is telling us how much money we lose if we make a speaker, or how much less than the optimal outcome we get. If here's what could really happen. Marketing says, look, we've got to make some speakers. That's going to fill out our product line, and we've got to at least have something in stock. Otherwise, so you can response from the manufacturing standpoint. Okay, we can make speakers. Here's how much it will cost us. Quantify it. Is it worth it? Maybe it is. Okay, but you can get that information out of the sensitivity analysis. If you want to really try this, you just go back to the model and say, okay, speakers, 801 instead of 800. And then we solve the model again. And sure enough, rounded, this is actually 25,000 and 1250 rounded out in formatting. That's what happens. We make exactly that much more money. Okay? Okay, now I'm going to run through a couple more examples, and the common denominator here is allocating resources, subject to constraints, maximizing or minimizing some objective. I don't want to spend the time. It'll take too long to explain this full model, but it's actually not that complicated. But this is a portfolio optimization example. So what's the resources? Move this over. The resources are cash that we're going to invest in 5 different stocks. So what are the decisions? It's how much money to invest in each of the stocks. And then there's 2 kinds of constraints in this model. One is called a budget constraint. Let me actually go over here to Analytic Solver Platform, and it'll pop up this window, and it'll say, we've got these 2 constraints. One is the portfolio, our allocations should sum up to 100% or 1. And the other constraint is, I want to earn at least 9%, and then I want to minimize risk. Okay? And if I just click this optimize button, it's going to tell me it's a quadratic model, which we can solve, and then then it finds an optimal solution, and so on. And so we allocate the money in that way to those stocks. Okay, I want to move right on to another model, 2 examples of it. This is a very important kind of model called a transportation problem. I have 2 factories shipping products to 5 different customer locations. And I can ship from any factory to any customer location, but there's a different shipping cost depending on what route I take. So I can send products from factory 1 to customer 2 at $225. I can ship from factory 2. It's a little further away. It costs me $250. Okay? And then I have certain demands from the customers at each location, and I've got certain supplies on hand at the 2 factories. So the problem is, how many do I ship along each possible route? All combinations of factories and customers, such that I minimize my shipping costs, but I meet the demand at each customer location. That's a constraint. So really, it's actually right here. Total received greater than or equal to demand. And then we also cannot exceed the supply that we have in the factories. So the total shipped out less than or equal to the capacity. Everybody with me on that? Here's total shipped out. Here's capacity. We're using defined names. Okay. So we solved this model, and I'm going to skip guidance here. By the way, I'll put this now in what we call expert mode to eliminate that thing altogether, all the prompts and messages. They're very helpful when you're trying to design a model. But here we now get the minimum cost of shipping, and it also tells us how many to ship along each possible route. Now, just to get a little more ambitious, on this one, it's a little more complex version of the same thing. We've got 2 factories. We've got 4 intermediate warehouses. We can ship from the factories to the warehouses. We can also ship from the warehouses to the customers. We've got 5 customer locations. And we also have 3 different products. Okay, everybody with me on this? And so we're going to solve the same kind of problem. We're going to figure out how much, but for every product, what's the optimal way to ship from a factory to a warehouse, or from a factory directly to an customer, or from a warehouse to a customer. It's just a more complex version of the previous model. The one extra element, it's the warehouse capacity in the middle. We have a constraint that says, we can't exceed the capacity of that warehouse. So we're just going to solve it right now. And sure enough, that was it, because we're in expert mode. It just solved, and it filled in. Let me actually undo that so you can see it. Okay, so down here are the decision variables. We start out with all zeros. We solve it, boom, and we come out with the optimal numbers to ship along all these locations. Okay? So what I'm hoping you're going to take away from this is, this is that old problem. This is actually, what a weird thing to come up. That is you can Google on that. That's a problem with Excel add-ins in general, and it applies to Solver. Some people are nodding their heads. They know about it. Okay. Let's back to where we are. Okay. So what did we learn? Hopefully, we saw that certain input cells, just containing numbers, served as decision variables. Other formula cells served as constraints, and we put bounds on them, lower bounds, upper bounds, or both, or equality constraints. We had one formula cell as an objective to maximize or minimize. And then Solver finds the optimal value of those decision variables. And importantly, the sensitivity report showed us changes at the margin. And that actually can be used for decisions like, how much should we be willing to pay for more speakers or more electronics units? Well, we have some guidance there. Okay. Now, these were all little sample models where all the data was on the spreadsheet, right? And that's not typically the situation. You've got to get the data from somewhere. Now, for a long time, it was true that these kind of models were built and the data was brought in kind of manually, right? So typically, you can see this, an optimization model is not working with like detailed sales transactions. It's working with summarized data, total sales or total demand or units or something like that. Those are the kinds of numbers we need. And in the past, people would get these numbers, from some source, and then they would copy them into the spreadsheet, and they start emailing that spreadsheet around, and so on and so on. Nowadays, we can do that automatically using Power BI or using Power Pivot, and taking the data directly out of a database and having it automatically summarized, typically in a pivot table, and then use that in an optimization model. So if you want to follow along with this one now, we're going to try to do the same kind of application. Looks like I got Excel closed here. Bring it back. And the one we want is actually this one, Power Pivot Tutorial Sample. And this is a 64 megabyte worksheet, so it's going to take a little longer to load. And we're going to enable content because that's a reference to the spreadsheet data model. Now, you don't have to follow along, but if you are, you should find that same, this workbook, Power Pivot Tutorial Sample, in the same folder as the others. Okay, so what do we have here? We have, how many people heard of the Contoso sample company from Microsoft? If you work with SQL Server, you've probably seen this example before. So this is Contoso, and what we've done is we have loaded, using Power Query actually, we loaded data into the spreadsheet data model in Excel. So just to show you that you can do all these things, you can pull data from all these kinds of data sources with Power Query. This is all free, from Azure, from other sources, all kinds, Salesforce, SAP, Hadoop, and so on. And then we pulled in this data. And then in Power Pivot, we can actually see what's in memory with us in Excel here. How do we do that? If you haven't used Power Pivot, just click this Manage window. It'll take a second to come up. If you have never done this, this is actually worth doing. And there it is. And so this is like a database view of the tables we have in here. And this one's a small one, but let's look at this fact sales table. So this is from Contoso. And I'm just going to scroll through this in Power Query. And you see the numbers there? We're at row 300,000 out of 2.28 million. And we can see all this data. So we've got all this data in memory with Excel. And a bunch of other tables here and so on. And if we go to diagram view, we can actually see what we've got in memory. And sure enough, here it is. So we've got a bunch of tables, and they're linked together. And this is the extra one we're going to use for the optimization model. And they're linked by keys and so on, right? So all that data is available. And then on here, I've constructed several pivot tables and pivot charts. And this is just, pointing and clicking in Excel to get that data. So the one I actually am interested in now is this worksheet here called Shipments by State. So if you click on that one, Shipments by State, and then go over to Analytic Solver Platform, it'll pop up this little model for you. And what we have here is we have another instance of this same kind of transportation model, this same shipment routing model, but we're driving it now from data that's coming out of Power Pivot through the pivot table. And so in particular, this grand total column here, which makes this pop up, I'll get off of it in a second. This grand total column, that's serving as our demand. Okay? So we are shipping from these regional warehouses, or from these, let's call them factories, Chicago, Dallas, Miami, Philadelphia, San Diego, and Seattle. And we're shipping to all these states and provinces in the US and Canada. Okay? And the demands, we're pulling from here. And the supplies, they're kind of simple. We're just getting them off of these fixed numbers here. Okay, and running this, same as before, click Optimize. And I'm in expert mode, so boom, it comes up with the optimal solution. I am trying to speed up here a little bit. I hope that's okay. I see some people are doing this. This is good, okay? So you see what you can do to put together, Power Pivot. And so this can be done with like standard solver. I could have solved this with just standard solver. It's not that big. The optimization model per se is not that big, even though the data is pretty big. We do have customers who are solving optimization models with like 2.4 million decision variables. And that's a more challenging problem and takes some extra software and special solver engines to do it, but we certainly can do it. And if there's one takeaway you take out of here, please make sure about this one. Don't let anyone, typically from another vendor or a consultant or something like this, don't let anybody tell you or convince you that in order to do this kind of thing, in order to build these kind of analytic models, you can't do it in a spreadsheet. I'm showing you that you can do it in a spreadsheet. I'm showing you can do it in Excel. So it's not that those other alternatives aren't good. Well, many of them are. SAS is an excellent product, and IBM has some excellent products and so on. But really, we can solve the same models because we're using the same algorithms and the same solver engines and the same statistical methods and so on in Excel as you can outside Excel. And because we have the ability to handle large data in Excel, it's a no compromise situation, using Excel versus using other tools. Okay. So hopefully what we saw here is we could get the demands and shipping costs from pivot tables. We did get the shipping costs from a pivot table. And we built a model, simple model, linear programming model. Oh, and there's one thing I didn't do. That's all right, I guess. There's a slicer on that same sheet. If you still got it open, you can just click on another year, 2007, 2008, 2009, and then just click Optimize again, and it will solve the model for that year. Okay, so you have all the flexibility of pivot tables working with the optimizer. And we could automate this, by the way, using VBA. Okay. So now, what's involved in, like if you go out and build an optimization model, what are some of the key things you need to learn to do? As you can see, there's not that, if you can build the what-if model, an appropriate what-if model that captures all the key decisions and all the key constraints and what the objective is, then it's just a few more steps, really, to define those things in Solver or in a more advanced Solver and then solve them. The main task, just like in simulation, the main task was defining probability distributions. The main task in optimization is defining the constraints. In this software, we have a constraint wizard and we have a distribution wizard for the probability distributions. But here are some things to just think about. One thing we saw is upper and lower bounds on the decision variables. That's the simplest kind of constraint, like non-negativity, right? Like a lower bound of 0. General constraints were like that inventory constraint. We were calculating how many parts we're using, and that's got to be less than or equal to our stock on hand. There were physical constraints, and we actually had one in that Transport 3 model where each intermediate warehouse had a finite capacity, and we had a constraint that was calculating, okay, what are we loading into that warehouse? Okay, we can't exceed its physical space. So that's a common kind of constraint. It's a matter of looking for these things in the business situation and making sure you include them in your model. And then we can have policy constraints. These are typically set by the government or by management or something, just things that we exclude from the possible solutions we can have due to policy. And then finally, understanding and presenting results is again, a very important skill to develop. So again, if you get used to just talking about what the model is doing and what kind of solutions it's yielding, you'll often get questions about, well, does this model really include this feature? And you have to be able to respond to that kind of question. Sometimes your model will not include some important element that somebody brings up, and you have to go back and revise the model and include that element in the model. But very often you can, and sometimes you can answer the question just from sensitivity analysis information. You can say something like, well, I don't have the value of having the full product line in the stores in the model, but I do know that it's going to cost us so much, $2.50 for every speaker that we make. Without that, because that's sort of the, now is it worth our while to go further and build a more complex model? Okay? All right, now, I want to try to show you, I'm going to skip this. No, I can't afford to skip this, it's too important. I'm going to show you what else you can do with optimization models using integer variables, and this is a very important element of integer variables. This is very important of modeling. It covers a lot of situations that you can't cover with regular continuous variables. That means decision variables that can assume any numeric value. So and I should say this too, using integer variables is a key skill in optimization modeling, and it's often an alternative to using if and choose and lookup functions, which can get you into trouble. So in this model, what we have is a truck that is delivering gas to customers. And there are 3 types of gas that, and we have customer demand, a different amount of demand down here for each of those 3 types of gas. And we want to, and if we don't meet demand, then we incur a penalty, and we want to minimize that penalty, and that's our objective. Okay, we're going to minimize our total loss down here. Now, the thing that's special about this is we have 4 tanks that we can put gas in, and each tank has a finite capacity. But the key difference here is that we can't put 2 types of gas into the same tank. Can't mix them. Okay? We can use more than 1 tank for 1 type of gas, but we can't mix, like fuel 1 and fuel 2 into 1 tank. Okay? And that's part of the model, and we have to express that. And so the way we express it is with these loading decisions. All of these cells here are decision variables, but they represent yes/no decisions. And so we're saying it's a variable, it can take on a value, but we're going to restrict its possible values to just 0 or 1. Okay, and 0 means we're not going to put fuel, 0 here means don't put fuel 1 into tank 1, and 1 means do put fuel 1 into tank 1, and then in that case, we'll have a finite capacity for that tank. Now that's down here. Let me do that again. And you can see it change down here. This capacity goes into place here. Okay, so now the problem is minimize total loss, don't exceed the capacities of the tanks, and make the loading decisions. Okay? So we'll go ahead and let this run. And I'm in expert mode again. So I immediately get this solution. And notice we're actually using tank 1 and tank 4 for this first fuel. And then we're using the other 2 tanks for these. And then we're respecting the capacities of the tanks, and we're minimizing our total cost. Now that's a very quick example, but this is a really important part of building optimization models. The need for integer variables arises all over the place, and you can define integer variables that can take on any whole number of values, 0, 1, 2, 3, 4, 5, 6, 7. And if you were like, for example, if you were building aircraft carriers, that should definitely be an integer variable. You can't build half an aircraft carrier. You can't, if you're assigning 100 people to some shift, it may not matter that that's an integer variable, even though you can't really assign a fractional person, but it's 100, so the difference between like a solution of 99 and a solution of 100 is you can round it. If you had a solution of 99.5, and you'll be pretty close to optimal. But when it's something like, do we open the plant or do we do not open the plant, you really have to model it as an integer variable. Okay. So what we saw from this, integer variables used to represent yes/no decisions. The way that's done in the solver, and I hope you saw that, is you just define the variable as a regular variable, and then you create a constraint that says this is a integer variable. So if we went to the standard Excel solver and just looked at this same model, here's what we'd have. We'd have the variables, loading decisions, and then we say equals binary. You just do that by selecting from the drop-down list here to bin. Okay? That's how you specify an integer variable. Okay. Now, we solved this problem very quickly because it's not that big of a problem. But the way the solver actually finds that solution is it solves a whole bunch of individual optimization problems where it kind of ignores the integer constraints. They're called relaxations of the original problem. Okay, so what we do is we say, the solver will say, okay, we're going to ignore the integrality restriction, but we're going to put a bound on these variables, first 0 to 1, and then 0 to 0, and then 1 to 1. And so it'll solve a whole series, a whole different number of problems with combinations of restrictions on the integer variables until it gets down to a solution where all the integer variables actually have integer values. In that process, it'll solve many subproblems where there is no feasible solution. It just discards those, and it will find other solutions where there is, it does satisfy all the integer constraints and the other constraints, and it keeps those around. Those are called incumbents. And then it finally, after it sort of exhausts all the possibilities, it comes back with a solution. Now, these problems can get very hard. And when I say that, I mean, for example, it's possible within even the limits of the standard Excel solver to define a problem that really has never been solved on the fastest supercomputers yet, even with very advanced methods. So these problems can get very hard. Many average problems, many typical problems, though, are solvable. And better solver engines actually can handle these. And there are lots of important problems in industry where there's 1 million decision variables and maybe all of them are integer and we can still solve it. So this is now we're in a domain where you can't make a black and white statement about whether your model is going to be solvable realistically or not. And the way you formulated your model is going to make a big difference. So this is just where you might need an expert consultant or something like that, or you just might need to learn a lot to make a model effective. But if you get to that point, you're probably already getting business results that make it worth your while. Other things about using integer variables, the sensitivity report is no longer available because there's no longer one problem being solved, there's many, and the marginal costs wouldn't apply. And so, as I mentioned, the integer variables make the problem much harder to solve. Okay, how are people doing on time here? I think we can make it. I'm going to go ahead and let me ask a question. How many people are interested in this issue about difficulties with formulating solver models, that if using if and choose and lookup functions in a solver model, why that's a problem? Okay, I got a fair number of show of hands, and probably the people who have used the solver. So I think I should go ahead and try and cover this. So I'm going to talk in general terms first, and then I just want to show you as best I can show you. Ideally, solver would always find the true globally optimal solution, just, period, given what the model defines, this is the best possible solution that satisfies the constraints. The mathematical reality is that this is only possible for certain models, and they're called convex models in general mathematical terms. Every linear programming model is a convex model. Some nonlinear models are also convex models. And in practical terms, it's only possible to find an globally optimal solution for smooth convex models. I'll elaborate on that in a minute. But what I want to really show you is what happens when we don't follow those, when we try to build a model that does include if functions, which make a model not smooth. Sorry, I closed Excel again there. And what I want for this is this worksheet, this workbook. Now, the way I would like to illustrate this is the following. I've got this product mix example again, the very first example that we looked at with the TV sets and stereos and speakers, but I've actually simplified it some more. So now there's only 2 products, TVs and stereos, and there's the same parts. And I did that so that I could actually graph the variables. So on the horizontal axis of this chart, I've got TV sets, and on the vertical axis, I've got stereos. Okay? Now, since I've got that graph, what I can do, and because the objective and all of the constraints are sum product functions, which makes them linear. If you actually just plot, well, I am just plotting them here, and they turn out as straight lines. Okay, so what I'm doing is I'm showing, so the orange line is actually the objective, and along that line, it's at that level on the chart, it's all the possible combinations of TVs and stereos that yield the same profit. That's called an isoprofit line. And what we want to do with that orange line is move it north. We want to move it, northeast. We want to move it up and to the right from where it is now. Right now it's plotting at 120, 120. Everybody with me on that? And then the constraints are, see the light blue one is chassis. And so for every point on that chassis line, we're making some combination of TV sets and stereos where we use up all the chassis. Okay? And so we cannot choose a solution that is north and east of that line. That's a bound. And same for all the others. Okay? So the light green one is speaker cones, and we've got to stay on that line because all along that line we're using up all the possible speaker cones. Okay? Now this is a simple linear programming model. We can go to standard solver, data, solver, same model, solve, and we get a solution. And you see how the line moved up? I'll actually, you see that? So the orange line moves up to here. I'll just solve it again and then save. So the orange line moves up until it hits the first one of those intersection points. Okay? Now it turns out that in every linear programming model, this also applies in general to convex models, this sort of thing happens. That is, you can have like this large number, infinite number of combinations of things. Solver doesn't actually have to look at all the possible combination of things. It does have to search. All optimization is a process of search. But it only has to search actually, up against, the edges, so to speak. Like if we were in more dimensions than 2, it'd become a 3 and 4 and 5 and 6 and then a 100-dimensional thing, but it would be a polyhedron, flat surfaces all the time because of the linear constraints. And solver just has to look for the corner points. And then it finds which one of those maximizes the objective. You could even be efficient at finding that. Now we're going to contrast this to a situation where we introduce some if functions. So what I've done here is exactly the same model, but in this one, I have, for the bound, I have, if we're above a certain number of TV sets, then amazingly, some of our, we get some more inventory. And the same thing here for electronics. So we just have a couple if functions. And then I've plotted them. And now they look like this. They jump. Everything is kind of moving along smoothly on those two blue lines, and then it jumps down to something else. Okay. Now, this is still a very simple example, but the solver has a challenge of trying to move that orange line up to the right spot. And I'll show you what happens. Let's use the standard solver again for this first. And we treat it as a linear model, even though it actually has if functions, which means it's not anymore a linear model. And we let it try to solve, and you've probably seen this message before. The linearity conditions required by this LP solver are not satisfied. So we can't use that, right? So we just change it. So we change to another solving method. We'll change this to the GRG solver, which is a nonlinear solver. And now it will do something. Comes up with a solution. And you see where it's moved the orange line to? It moved it to this intersection point. We're making 100 TV sets and 200 stereos, and we're earning $17,500. Looks pretty good. A lot better than the linearity conditions are not satisfied. But how confident are you that this is the optimal solution? Obviously, this is a setup, right? But indeed, this is not the optimal solution. And it all has to do with the jumps introduced by the if functions. Okay, GRG solver doesn't realize that it can actually jump up further and still have an optimal solution. Now we have some magic to deal with this in Analytic Solver platform, and we're going to go ahead and let it solve this problem. I should set it back. I think we started at 120 and 120, to be fair. Okay, so we're down here. We'll let this thing solve. And now I'm going to turn on, well, first of all, let me just let it solve. And sure enough, it jumps up to the higher point. But I want to actually undo that and show you what happened, because that's kind of a amazing result. And it does not happen easily. So, okay, we have guided mode on now. We click optimize. It comes up and says, welcome to guided mode, etc. And it's looking now at the algebra. It's looking at all the formulas, and it's finding the if functions. And it's saying your model is a non-smooth model, most difficult type to solve. Probably you're using if, choose, or lookup functions. What we could do is we're going to try to algebraically transform this model. Sometimes we can do it, sometimes we can't. In this case, we can. Boom, it says we changed the formulas, okay, internally inside this solver. It got rid of the if functions and replaced them with additional integer variables, binary integer variables, like we saw before, representing yes/no decisions, and additional linear constraints, and turned it into a larger linear mixed integer problem. And now it's poised to solve this. You've got the nonlinear solver. That's not the best choice. We've got all these other solver engines. We'll pick this one. Go to the next step, and boom, now we find a solution. And then we just plug it back. We're solving the extended, the transformed problem, and then we plug it back into the original problem. The real point of this, though, is look how different the solution is. 50 and 325 and earning $20,000 versus what we had before and earning 17,500. Pretty big difference. And that's just to show you that this is an important issue and you can't ignore it. So in general, what I would recommend is trying to learn how to model with integer variables and not use if functions and choose and lookup functions yourself. There are some tools, we've got some and some other people do, to make an automatic transformation. But it's even better, I think, for people to learn why this matters and what they can do about it. Now, real quickly, without going into a lot of detail here, in general, for a linear programming problem, which is known to be convex, we find the globally optimal solution. For nonlinear problems, if they're smooth, no if functions and things like that, we can find a locally optimal solution, and if it's convex, globally optimal. And the evolutionary solver can be used on any model, but all it's going to do is find a good solution. And so what does it mean for a model to be linear? Sum product and sum are basically what you can use. You can multiply variables by constants, and you can add them up and subtract them, and that's it. One important point, when I say you can multiply variables by constants, it can still be something that you calculated in your model with a formula, as long as the whole formula tree with all of its predecessors doesn't depend on the decision variables. That thing is still constant as far as the optimizer is concerned. Everybody with me on that? And what we're doing in the analytic solver platform is we're actually analyzing the formula tree and finding that out, finding out what things depend on. But it's possible for you to just to plan your model so that it turns out to be a linear model. And it's often true that the same business situation, the same real world situation, you could build a model for it that's linear, and you could build a model for it with if functions, or you could build a model with linear and integer variables, or you could build a model with if functions, and you'll get better results in the first case. Nonlinear optimization, you can use essentially any smooth differentiable function or operator like these, not if, choose, and lookup, get a locally optimal solution, or sometimes better. And then non-smooth models, you can do anything that you can do in Excel, but solver can only find improved solutions. This is the evolutionary, it's genetic algorithms. We also use taboo search and some other methods. And it actually has no way of testing whether you're at an optimal solution. There's just no basis on which to make that test because it involves computing derivatives. And for that reason, it doesn't really have a hard and fast rule of when to stop. And so it only has heuristics. It has basically, it says, well, we haven't made any progress for a while, so we'll stop. That's the kind of thing that has to be true. Again, it's not just solver in Excel. It's not just some other, like the nitro solver in AMPL or GAMS or something. It's intrinsic to the mathematics of these problems. And then finally, I want to give you a sense of what happens when this scales up. So in this little model, if you remember in Excel, the little kind of kinks in the graph, when we just introduced these two if functions, right? Well, you can think of those like, the solver is, optimization is a process of search. So we've got to search our way around those kind of nooks and crannies created by those jumps, right? And when a model scales up in size, this is what happens. So on the left here, your left, is simply an objective in two variables with a very complex shape. Solver has to find which is the highest peak among all those peaks, or which is the lowest valley, at the bottom somewhere. That's not so easy to find. And if that were not two dimensions, not two variables, but 100 variables or 1,000 variables, it gets pretty hard. That's just a non-convex objective. The other two charts, which are literally mazes, are just a kind of an analog for what happens when you have non-smooth functions in your constraints, and you're creating all these paths that solver has to search among. It's pretty hard. And what happens is, as the size goes up, the complexity goes up exponentially. So these are actually NP-hard problems, if people are familiar with that. So that's hard. Now, you may still say, well, come on, it's 2015, we got a lot of computer power. Why can't we just do this? Let the computer exhaustively search. Let it find its way through the maze. Well, quantify this a little bit. Suppose your model has 5 years by month, so you've got 60 periods, and you have one if function in each period. So you have 2 to the 60th, right, combinations of true and false decisions for those if functions, 2 to the 60th power. You can put that into a cell in Excel, and it comes out to 1.15 e to the 18th power. Now, how big is that number? We usually don't have a sense of it, but I have a comparison here. So the outcome is if you started solving that problem with only 5 years by month, and you started solving it at the time of the Big Bang, you'd be halfway done by now. So my point, obviously, is you can't just say, why is my computer fast enough? You have to deal with, it's so easy, really, to build a model that is unsolvable, and not just this year or next year or even the next, maybe, I don't know what will happen in 100 years. But anyway, so that's why. Okay, we are at 5:28, so we're really kind of at the end of the time. I will keep going for everybody who's willing to keep going, but if you have to go, that's perfectly okay. All right, so we have one more topic we're going to try to cover, and that is we're going to try to combine simulation. We're going to try to combine real uncertainty, dealing with uncertainty in our model, and making optimal decisions in the presence of that uncertainty. And we're going to open up some deeper issues, okay? So what are we going to do? The problem is we're going to allocate scarce resources when uncertainty affects the objective or the constraints. So what's going to be in this model? We're going to have input parameters that we cannot control, just like before. We're going to treat those as uncertain variables. We're going to describe them with probability distributions. Then we're going to have other parameters that we can control, which are our decision variables. And then we're going to have formulas that may depend on both. So our objective or our constraints may depend on uncertainty, and they have our decisions in there too. Okay? So now, first thing to think about, what does it mean to maximize or minimize our objective when it depends on uncertainty? And the reason I ask this question is, what is this? So we're calculating something, and we saw in simulation that we get a whole frequency chart, not just one number. For any choice of number of tickets sold, we got this whole distribution, right, of possible outcomes. So we can't maximize or minimize that. We have to maximize or minimize some statistic or some function applied to that distribution. So, and the most common one is the mean. So what we were doing earlier is we did an optimization, and we took the mean value, which is just the average, or in other words, the average across all the Monte Carlo trials. We used that as the thing we were going to maximize or minimize. So that's the first issue we're going to encounter. So let's look at a model where we do that. Let's see. We want these, and we can close the other one. Okay. This is a model where we have, this is a capital budgeting problem. We have 8 projects that are competing for funds. And each one has a fixed known initial investment cost, and then it has an uncertain future. And our problem is to decide which of these projects to fund. Now, right now, we have, these are going to be our decision variables, and they're going to be 0, 1 variables, yes, no variables. Right now, they're all ones, which means that we fund all these projects, and that totals up to 2.5 million, but we've got a budget of 1.5 million. So we can't do that. Okay, so we have to pick among these projects to fund them. Now, if we fund a project, then in this model, the project might succeed or fail. And we're modeling this with, let me go to Analytic Software Platform here, and it'll show us the model over here. So each one of these can succeed or fail, and we're modeling that with a certain kind of discrete probability distribution called a binomial distribution. So we have a 10% chance of failing and a 90% chance of success. Not too bad. But then, if the project succeeds, then we get a varying amount of cash returned from that project. We're modeling that with these triangular distributions. So this one goes from a low of 500,000 to a maximum of 1.2 million, and the expected value is 750,000. So every one of the projects is like that. Okay? So I'm just going to go ahead and solve this model. First, before we solve it, we're just going to run a simulation on this problem. Okay, and so we're doing just what we did before. And we get a distribution of outcomes for total cash flow. Okay, so we had this outflow of 2.5 million in total, and then all the projects did what they did. Some failed, some succeeded, depending on which. We did 1,000 scenarios of this. And projects succeeded and failed and generated some amount of cash, and then we got this net result. Okay? Now what would we like to do? We would like to maximize what? Not this, because this is a distribution, but sine mean of that. In other words, the expected value of the total cash flow is what we would like to maximize. Now I can do this manually. Let me try. My first problem is to get under the budget limit. So let me just start taking out projects. We're at 1.9 million. Still not quite there. Okay, now we're under 1.5 million. And actually, if I run a simulation on this, I'll know what my outcome is. About 1 million in total cash flow. Okay. Now that's probably not optimal. So now just to go do this quickly, I'm going to let the optimizer, I'm going to let Analytic Software Platform actually solve this using all of its tricks. And it's going to, well, let me just show you. It'll say, it's got a model with uncertainty in it, able to transform it into something called the stochastic programming deterministic equivalent, and we're able to solve it. And then these are the projects that we pick, which ones to fund and which ones not. And if we run a simulation at the end, then we get this outcome, and we actually make a little closer to 1.4 million. Okay, so that's the kind of problem we can solve. Now, how are we able to do that? These problems are very difficult to solve, and actually, I use this as an example because there are naive ways and there are sophisticated ways to solve it, and Analytic Software Platform was able to figure out the sophisticated way. But the reason why we could solve this particular problem as easily as we did is because of these three things. The uncertain variables didn't depend on the decisions. I'd like you to think about this for a minute. So which projects we fund, we pick them, but those chances of success and the cash flows that follow don't change just because we pick project 1 and project 3 and project 7 and so on. There's independence there. There's lots of real-world problems where that's not true. And there are other problems where it is true, where you have independence between the uncertain variables and the decision variables. The other key thing is that the budget constraint didn't depend on the uncertainties. It was, the year one costs were all known, and the objective was linear, and we took an expected value, and for that reason, it reduced to a simpler problem. I'll ask you a question about this first issue of uncertain variables depending on decisions. Suppose that you, as an individual investor, and I'm assuming there's no billionaires in the room, suppose that you decide to buy a certain stock. Is that going to change the future returns or the uncertainty around the future returns, like the distribution of returns? Is your buying that stock today going to change what's going to happen to, let's say, a Dow 30 stock? No. I mean, you're too small. I mean, you're not going to have an impact. So in that scenario, you could say, yeah, uncertainties are independent of the decisions. But suppose now that you're I don't know, Fidelity or somebody, Fidelity Management, and you're buying a small cap stock, and you're buying 2 million shares. Now you ask that same question, you get the opposite answer, right? I mean, you buying that stock is very probably going to move the price, and therefore the future returns are actually going to be less. And you have to deal with that. And there are people who build models that deliberately incorporate that effect. So it's something you need to think about when you're trying to deal with a optimization problem with uncertainty. The second thing is we have not yet seen a problem with a constraint where the constraint was subject to uncertainty. So we talked about the objective, but now what happens if we have a constraint that depends on uncertainty? Well, the constraint is no longer a single number. Even for any given set of values of the decision variables, it's no longer a single number, it's a distribution. And often it's a distribution with infinite tails. And so now we have to ask, what does it mean to satisfy that constraint? Because it's not always going to be less than some fixed number. So that introduces the need for the notion of soft constraints. We call them value at risk constraints. So we're going to satisfy, or they're often called chance constraints. So we're going to satisfy a constraint not with certainty, but with a high probability. Okay? Now with those ideas, let's take a look. Here we have a model of a gas company. This is like a gas utility. And what it does is it purchases gas from available sources, and then it distributes the gas to customers, very simple. And its key requirement is it's got to meet demand from the customers. We don't want people to run out of gas. Now it's planning over a 2-year horizon. You see year 1 and year 2 on the spreadsheet here several times. In year 1, the price of gas is fixed. It's $5 per unit and known. No uncertainty about that. And the demand is also known in year 1. That would make sense. In year 2, the price of gas and the demand for gas are uncertain. Okay? And in fact, the underlying uncertainty, is being modeled here, and we're using something called a beta distribution. And you can think of this as essentially modeling the weather, and then we are computing the demand in year 2 and the price in year 2 based on that. And as you can imagine, when on a cold winter, the price goes up and the demand goes up. Okay? So now the company has the following choices. It can buy a certain number of units of gas in year 1 and distribute them immediately to consumers. It can buy some units of gas and store them in storage facilities, incurring a storage cost, and then have that in year 2 and distribute that to consumers. Or it can buy gas in year 2 at whatever the future price is, we don't know it yet, and then distribute that gas to consumers. And then the two constraints are meeting demand in year 1 and meeting demand in year 2. And then our goal is to minimize the expected total cost over all the scenarios. And the thing that's unique or different about this model is this constraint here, which is on C23. We're trying to keep it greater than or equal to 0. That right here. This is our where we need a chance constraint. And so we've said we want to satisfy that constraint with 95% probability. Okay. And we can actually click this in. I can't do that, but let me click this and run a simulation and see that's actually our distribution of costs that we're trying to minimize. In a minute, we'll be able to get a chart of the constraint. So I'm going to go ahead and let it solve. And let's see, hopefully we have, we're in guided mode, so you can sort of see what it's doing. So welcome to guided mode. We find out that this is, the previous slide actually showed us that it found out that this was a model with uncertainty. It's able to transform it into its robust counterpart. So we're using robust optimization. Then we find a conservative solution to it. And just to show you we can do this, there's a little extra feature here where we can improve on that solution. And then we get this. And at the end, we're going to run one simulation at the end to see the results. And that's the objective. And we're also interested in looking now at this constraint in year 2. And you can see that it's getting satisfied almost all the time, but not quite all the time. So we're going a little bit below 0 there. Okay, now this is really just showing you that we can do it, that we can actually solve this kind of problem using chance constraints, and we can get a solution, and we can, this allows the company to plan. Notice what we've achieved, though. We've achieved an expected total cost of 1.446. Just remember that number for a second. Now I would like you to think about this. What's going on here, really? We want to satisfy demand with 95% probability. That's a pretty high threshold, and it's going to cost us. Okay, we're going to pay for we're going to be conservative. That is, we're going to buy more gas. We're going to pay more for gas, either buying it, or in year 1, or storing it, or buying it in year 2, in order to make sure that with at least 95% chance we're going to meet demand. Maybe that's all we can do. But let's really think about the underlying problem here. So I'll sort of ask you the right question. We have 3 decisions. One is how much gas to buy in year 1, and how much gas to buy and store in year 1. When do we have to make that decision? Year 1. We've got to do it now, right? What about the final decision? How much gas to buy and resell in year 1? The amount of gas to buy and sell in year 2. When do we have to make that decision? We don't. Yeah, we can make it later. We can make that decision on a wait-and-see basis. Okay, that if you think about the business situation, unless for some reason our supplier requires us to specify in year 1 how much we need in year 2, generally we could wait until year 2. We won't know what the price is, and we won't even know what demand is, but we could wait and see on that decision. That's called a recourse decision in stochastic optimization. And so what we're going to do now is we have another tab here where we have exactly the same model with exactly the same formulas, and exactly the same distribution for uncertainty and so on. And the only difference is, on the model tab here, we have turned this one decision variable into a recourse decision. We just changed it, and we have a drop down for that. And so now we're going to make that decision on a wait and see basis. And if you think about it, we're going to run 1,000 Monte Carlo trials, and we're going to get 1,000 different optimal values for that decision. And we're going to get one optimal value for the first two decision variables, the here and now decisions. Okay, so if we go ahead and let this run, it'll tell us what it finds, and then it's going to transform it into the stochastic problem, give a deterministic equivalent, and solve it. And again, we'll run a simulation at the end. And I don't need the rest of that chart, but notice where we come out. We come out at 1.295 versus 1.446, right? So we've been able to improve our overall objective by a fair amount simply by changing the when we make the decision, right? Really, what we did here is we recognized something about the real-world business situation, namely that some decisions are here and now, and others are wait and see. And then we built that into the model. And then we let the optimizer take advantage of that. And what really happens here is that the recourse decisions buy us flexibility for the here and now decisions. We don't have to be as conservative up front because we have this recourse action we can take later. Okay? Here's a classic example of this kind of problem. You're planting crops. And you can plant soybeans and wheat and other things. And each one responds differently to the amount of rainfall we get. And then each one has a price. And we have so much land we can use and so on. So if that's all I tell you, and I want to maximize my result, then you're going to take into account the yield on. Essentially, you're going to have some estimate of what's going to happen with rain. That's our uncertainty. And you're going to make some kind of result saying, well, if we get a really dry season, then really corn's going to be better, because it can survive with less rain. I don't know. And so on. You're going to have to essentially come up with a conservative solution in order to kind of stay in business. But think about really planting crops in the real world like they really do in the California, valley and, in the middle of the state and so on. What do they do when it's a dry, season? Irrigation, right? I think somebody was saying this. Irrigation is a recourse decision. Irrigation is, okay, I didn't get enough rainfall, so now I'm going to pay extra to get some water in through the irrigation lines, but that's going to cover me for those outcomes when we had a dry winter. So, and what does that let me do? It lets me, be a little more aggressive up front in what crops I plant and get an overall better result. So you will find this is a very important question to ask if you're ever doing simulation, or if you're ever doing optimization modeling with uncertainty. What are are there recourse decisions available? And if so, let's make sure we model them because it will make a big difference. Okay, you guys have been really, really patient with me and everything, so we're going to wrap up now. You saw what we did. In the chance constrained version, we satisfied a hard constraint in year 1 and a soft constraint in year 2. Then we moved on and said, well, what if we could postpone the decision in year 2? We did that, and we found we could get a better objective, lower total costs, because the recourse decision bought us flexibility. Okay, you guys are now like way ahead of most of the people, actually most people even doing optimization modeling at all, because most people don't get this far with stochastic optimization. They pretty much do conventional optimization. So, can this help you in your working career? I mean, I hope you're convinced already, but I will just point this out. It just really happens frequently, and the bigger the company where you're doing this, typically the bigger the impact. Optimization models can deliver very significant cost savings, and simulation models can basically keep you out of trouble. So if you're a big enough bank, this really matters. I mean, ever since 2008, 2009, it's definitely got a lot of attention, and we're still in that kind of world right now. Optimization models, this is a real story. Prior to 2008, when things kind of fell apart in mortgage finance, we actually had a customer they're now part of Bank of America. But, Bob, who am I thinking of? It's Countrywide Financial, thank you. It's like now we kind of want to forget about them, because we all know what happened. But in their heyday, Countrywide was the biggest originator of mortgages in the nation. And what they were doing, of course, is they were originating mortgages and then pooling them. They were putting them together into mortgage-backed securities, and then they float those securities on Wall Street. And they get a certain yield, and then then they get the money from floating the bond issue, the mortgage-backed security, and then they originate more mortgages. Well, they were building a model, an optimization model, to pool the mortgages into a mortgage-backed security. And it's based on getting a kind of an optimal distribution of credit quality and geographic diversification and so on in these mortgage-backed securities. That was the model. And they were really excited because I think they were getting 5 or 6 basis points improvement in yield on these mortgage-backed securities. Now, I think I already see some people sort of smiling because if that were your bank account or mine, 5 basis points is 0.05%. Who cares? But if you get to multiply that number by several $billion, it's a big number. So what happens with these optimization models very often is the bigger the company, the bigger the potential payoff. And where this is not being done right now, there's a big opportunity for people who can do it. So if you can do it, we've seen this with a bunch of our customers who have really seen their value to their company rise. It's definitely worth knowing something about. A general comment here is we looked at some analytic models here that address operational decisions, logistic decisions and things like this. There are some optimization models that very much address strategic decisions. Whether to enter a new market even, whether to open a new plant, we've seen people do things like develop a plan for hiring and firing thousands of people, or hiring and firing and training thousands of people. So these can be big decisions, and you really should try to apply quantitative methods because the stakes are so high to these kinds of decisions. So if you're going to do this kind of work, it really does, it's kind of advice, be prepared to present your work to senior management and help them understand and be willing to come back and say, when they're asking hard questions, that you can either respond to those questions or go back and do another round, on the analysis. Okay, wrapping up now. Where to learn more. These are some textbooks that we like. We like them partly because those textbooks are really good, but we also, by the way, all 4 of these are textbooks that are very popular in MBA programs where they teach this stuff. There are quite a few others. These we like. There's like 35 or 40 books where they use our software, but these books are kind of all relative bestsellers, and they use Analytic Solver Platform, the software we've been working with, throughout the book. And you can actually get these books and get a free trial license to a size-limited version for a period of time. So, and you can find all of these on Amazon or in a college bookstore. They're not cheap. These books, I think the blue one, Management Science, is usually the best price on Amazon. It might be like $80 or something, but Cliff Ragsdale's book on the left might be like $220 or something like that. Still relatively good deals. And then finally, you can learn more from our website, solver.com, or our YouTube channel. You're welcome to go there. And there are links, like on this second tab, Optimization Excel Solver and the Monte Carlo simulation. There are links to the free versions of like Solver and Risk Solver for Excel Online and Google Sheets and so on. So one final thing I'd like to leave you with. If you go and try this, and I really hope you will, I hope you really give it a go, do this. We've seen too many people get excited and try to do the super ambitious, like save the world type of model the first time. And I really highly recommend this sort of maxim, do something small, simple now. Get results as early as possible. If you're building a model that's going to ultimately involve, 50 plants and 100 distribution centers and hundreds of products, start with a small one, prove it out, and you might even a lot of companies, they'll do pilot projects where they'll actually implement the system in a region. We're pretty friendly with UPS, and they're excellent users of optimization methods, and they will do things like they'll try out a new algorithm in just a city or just in a region, something like that, and prove it out in the real world before they go, national or international with it. So it really pays to start with a small instance of your full-scale model, and then when you've proved it out, scale it up. Get quick wins, show that you can get some results. That will typically build organizational support, both from like peer level people and senior management, and then you can move on to bigger things. So, okay, so that's it. I hope this has been helpful to you. You've been a really great audience. I mean, I really appreciate your sticking around. And there haven't been too many, there really haven't been any live questions, but does anybody have any questions now that I can answer? Yeah?
Can you go back to the book slide?
Yeah. Anybody else? I think everybody's getting about ready for dinner or refreshments or something, right? So we have an exhibit over in the exhibit area if you do have questions, and we'll be happy to take questions there. Oh, did you get that? Anybody who wants to get it? Okay, I'm waiting for, okay. And then here, the final thing is simply this one, session evaluations. It's pretty much the same for every session, but please do, again, because this is a hands-on lab, it's really helpful for PASS to get the feedback. And thank you so much for coming by. I want to sort of applaud the audience here. Thanks much.